Hello there, friends. Welcome to episode 12 of Math 141 Recitation, Summer 2020. As always, it's your host, Bailey, here at JBH Math on YouTube. Today we are talking about monotone functions in the first derivative test, section 4.3, and we are monotone deaf no more. Indeed, now that we are experts on monotone functions, we are no longer monotone deaf. Get it? Like tone deaf? Ha 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 ha. Since this is a relatively short homework assignment with just the one section, section 4.3, I decided to also throw into this video a couple of review problems, which Mackenzie mentioned were challenging. So first we'll do a derivative rules problem, and after that we will move on to a related rate problems. I imagine that you've seen both of them if you've been working on the homework, but we haven't done any of them in detail in any of these videos, so they will be excellent practice for us. They will also be great review for your exam this coming Thursday. So why don't we go ahead and get started? So I'm actually refilming this. I recorded it about 15 or 20 minutes through until I realized I had made a big silly in the second problem. So I decided to just restart. So the first problem, I've already written everything out, but we'll go through it slowly. And then the second problem, we will write everything as we go for the most part. So this first problem, I don't remember, it was on one of the homeworks. I don't remember the exact problem number. But the problem says, suppose u and v are functions of x that are differentiable at x equals 0. And then it gives us 4 key pieces of information, which we'll use throughout the problem. First, we're told that u of 0 equals a -1, and u prime of 0 equals -9. We then have that v of 0 equals 9, and v prime of 0 equals +1. So we've got a little bit of symmetry here with u of 0 is -1, v prime of 0 is +1, and kind of similar things with u prime of 0 and v of 0. So then we are going to find the values of the following derivatives at x equals 0. So 2 comments here. One comment is that it's very important that we are looking at x equals 0 here. All of the information which we're given, right, u prime, we're given these specific values, and all of these specific values which we're given are values at x equals 0, right? So if the problem said, find the values of the following derivatives at x equals 1, we wouldn't have any idea because all that we know about these functions is we know a little bit about their values. In fact, we know what their values are at x equals 0, but we don't know their values anywhere else. Now, if the problem said, find the values at x equals 1, and the information was given to us at x equals 1, of course, then we would be in fine shape. The point is that it's important to note that that what it's asking for is consistent with the information it's given us. Of course, I think most problems which you encounter in a math class will be that way, but it's still worth appreciating. The other comment, and I kind of touched on this, is that really one of the cool things about this problem, this is such a cute problem. I love this because what we're going to see is we're going to be able to find all kinds of information, and we don't even know what these functions u and v actually are. All that we know is their value at one particular point. So this shows how using just a little bit of information can actually go a pretty long way sometimes. So without further ado, let's jump into it. Part A, there are 4 parts. The first part asks us to find the derivative of uv, so the product of these 2 functions. And this should strike you immediately as a product rule problem. Product rule very appropriately named. We're taking the product of u and v here. So let's go ahead and take their derivative. So the product rule tells us that the derivative of uv is going to be u prime of 0 times v of 0. So we're going to take the derivative of 1 and leave the other one alone. Plus, now we're going to leave u alone and take the derivative of v. Okay? Now again, you might say, well, I don't know what v prime is. Heck, I don't even know what v is. But thankfully, we don't need to know v prime is a function. We just need to know its value at this one particular point. So we have that information. We go ahead and plug in our values. We end up with -9 times 9 plus -1 times 1. All that I've done here is substituted the values from the information which we were given above. So we make those substitutions, and then we just do a little bit of computation, and we get our nice solution. I think this problem looks very scary because it's very abstract, right? We're not given specific functions or anything like that. But as I hope you will see, it's really not going to be so terrible once we break everything down. Part B now asks us to find the derivative of u over v of the quotient u over v. So that brings us to another appropriately named rule. We're going to use the quotient rule this time. Now the quotient rule tells us, now this one is a little bit easier to get confused, so definitely make sure that this is one that you're comfortable with. So this tells us that the derivative of u over v is going to be, let's see, in the numerator we'll have u prime of 0 times v of 0. So we take the derivative of the numerator and multiply it by the denominator. And then we subtract the numerator times the derivative of the denominator. So I think I've said this before, but notice in the product rule, if I wanted to, I could instead write u of 0, v prime of 0, plus u prime of 0, v of 0. In other words, I could, if I wanted to, I could flip these two things, right? These two quantities. Because whenever you're adding, it doesn't matter which way you do it. What makes the quotient rule trickier is that I cannot just flip-flop this numerator because, for example, 2 minus 1 is most certainly not the same as 1 minus 2. So it is very important here, and that's what makes the quotient rule trickier. In the denominator, we just square the original denominator. So again, all that we're going to do next is we just plug in the values which we are given. Okay, this is a 9 down here. This kind of looks like a 4. What happened was I accidentally wrote a 1, and then I tried to just correct it. But there we go. That's a 9. So again, we plug in our values, and we do a little bit of simplification. Okay. Now, we basically do the same thing for part C. We are instead asked for v over u rather than u over v. So we've just flipped it. So again, it's the exact same formula. We've just flip-flopped the places of u and v. It works just the same. You plug in your values and you get your solution. Now it's worth noting here, and again, I trust that you can work through the details yourself or pause the video if you need to and work through them. But notice that the derivative of v over u, I can't just flip the derivative of u over v. Right? They both have like 80s and stuff. But it's not just like 1 over. I can't just flip the derivatives. Right? I flip the function. But whenever I do that, I cannot just flip the derivative. So that's an important thing to note with regard to quotient rule. Finally, part D asks for the derivative of -5v minus 6u. So I went through and I broke this down in excruciating detail, right? So first we can distribute that derivative to both of the two, the two functions, since we're just adding them or subtracting them in this case. Then we can pull the constants out front of the functions, right? So I can pull that -5 out front of the d dx from the v. And same thing with the 6 for the u. And then I just rewrote using notation that was a little bit easier to follow, right? So -5 times v prime of 0 minus 6 times u prime of 0. And once again, just plug in your numbers and compute. Now, especially with part D, parts A through C, I don't think there were really many shortcuts you could take. In part D, though, if like this first step here, like if this up here, and even this are a little bit too redundant for you, you are more than welcome to go ahead and start at this third line here. That is totally fine with me. At this point, honestly, I think it would be a good sign if you feel comfortable going straight to this point. Again, here I figured I would show all the details just to be crystal clear. But in reality, you're probably going to want to skip maybe those first couple of steps, assuming you are comfortable. If not, by all means, do what you need to do to get things right and take your time. Okay, so that is our derivative rules problem of the day. Unfortunately, sad face, no chain rule in this one, but I bet you we will get some chain rule at some point today. Okay, that brings us to the second problem. This one is very long to write out, so I'm actually quite glad that I'm not going to write it out again in real time. So this problem, we are told that a balloon is rising vertically above a level, straight road at a constant rate of 4 feet per second. Just when the balloon is 68 feet above the ground, a bicycle moving at a constant rate of 20 feet per second passes underneath it. How fast is the distance s of t between the bicycle and the balloon increasing 3 seconds later? Wow, holy mouthful. I thought this was math class. What are all these words here? Let's take a look at the picture. This is the picture that they gave us, and I just sketched a simplified version of it. So we've got this right triangle formed. The height of the triangle is the function y of t, or it's y, but y depends upon t, right? The height of the balloon basically is what y is, so that depends upon time. The length of the base is x of t, or basically that's just the distance that the bicycle has traveled since it's passed underneath the balloon. And then our hypotenuse is this distance s of t. Why do I keep doing that? This distance s of t between the balloon and the bicycle. Okay. So the first question really which you want to ask yourself virtually any time that you have one of these related rates problems is, okay, I got all this stuff going on, all these numbers, I got balloons, I got bicycles, what the heck am I actually interested in? And so what we are interested in, I already underlined it from earlier, from my first blooper, I guess. We are interested in how fast s of t is changing. Okay, we are interested in how fast s of t is increasing 3 seconds later. So what we want is ds dt, the change in s over change in time, at t equals 3. Okay, the 3 comes from the 3 seconds later. Okay, so by later, they mean 3 seconds after the bicyclist has passed underneath the balloon. So we want ds dt at t equals 3. Well, why don't we go ahead and see if we can come up with a nice formula relating all of our quantities. So we have this right triangle, x of t, y of t, and s of t being these sides. And so from that, our boy Pythagoras, he was hardcore. I would love to tell some of you guys some of the fascinating things I've heard about him. Basically, he had somebody murdered because they tried to prove that the square root of 2 is irrational. And Pythagoras and his basically cult following were not fans of that. They were right, of course. The square root of 2 is not rational. Pythagoras just didn't want the truth getting out there, I suppose. Anyways, wow. So sometimes whenever I feel like I love math, I think, you know what? Do I really love math? How many people have I killed over their claim that that a number is irrational. Okay, so in any case, one thing he did do well was he could darn well compute the sides of right triangles, and so this theorem gives us that s of t squared, the hypotenuse squared, is the sum of the sides squared, right? S of t squared equals x of t squared plus y of t squared. So now we take the derivative with respect to t. Why are we doing that? Or how do we know to do that? Well, we know that we want to introduce the quantity ds dt somehow, because that's what ultimately we want to compute. And so taking this derivative is exactly how we'll get that done, because then we get 2s ds dt equals 2x dx dt plus 2y dy dt. Remember, we throw in these dx dt's, dy dt's, ds dt's, because x, y, and s are all functions of t. So whenever we take this derivative, this is basically the chain rule coming out. We have to multiply that by, multiply each of those quantities by their respective derivatives. Now, we want to find ds dt, so we can just algebraically manipulate this. Okay, you're allowed to manipulate algebra, but do not manipulate people. Okay, manipulating algebra, good. Manipulating people, bad. Okay, say it with me, thank you. ds dt. All right, so now we have a nice formula for ds dt. And it's nice in the sense that it's isolated. You know, we can we manipulated it to isolate it. That is something you certainly cannot do, folks. Do not manipulate people and then isolate them. That is, oh boy, that's a major, major red flag. In any case, it's nice in that we have ds dt all alone, but on the other hand, man, we got all these variables that we need to solve for. We got x, dx dt, y, dy dt, and s. So why don't we go ahead and see if we can figure out what those things are. Well, dx dt, so that's going to be the change in x, right? So that's going to be how this bottom side is changing over time, that rate of change. And we can see that that's just going to be the speed of the biker, right? The rate of change of x, well, that's just asking how fast is the biker going. So this is the speed of the biker. Okay. And we are given that, I believe, right? Yes, the bicycle is moving at a constant rate of 20 feet per second. It's great that it's constant because then we don't have to worry about this whole 3 seconds later business, right? Remember, we want this derivative at t equals 3. But since this rate of change is constant, it doesn't matter whether t is 0, t is 20, or t is 1,000,000. It's always, the dx dt will always be 20. dy dt then is similar. It's basically the same idea. This is going to be the speed of the balloon. Right? If you look at the picture again. Well, the height here of this triangle, that's just changing as the balloon rises further up. Now the balloon is rising at a constant rate of 4 feet per second. So dy dt is going to be 4. Okay, now let's look at x. Well, x is going to be the position of the biker. Right, if we look at this picture here, the length of the base is just how far the biker has gone. Okay. Well, the biker is going 20 feet per second. And this is important, we want this at t equals 3, right? We want ds dt at t equals 3. So it's going 20 feet per second. And then we want it to go for 3 seconds, not 3 seconds, 3 seconds. So that gives us that x equals 60. Similarly, y is going to be the position of the balloon. Now here we're going to have to be a bit more careful, not balloon. Here we're going to have to be a bit more careful. So it is rising at 4 feet per second times 3 seconds. But, and this is actually where I made the mistake last time, and I realized it too late. The key, or the important observation, is that at time t equals 0, the balloon is already 68 feet above the ground. So we need to add in those 68 feet. It started 68 feet up, and then it went these extra, it looks like it's going to be 12 extra feet. So that gives us 80 feet. Okay. All that's left to find now is S. So S, well, we have a formula for S squared up here with our Pythagorean theorem. So if I take the square root of that, of both sides, then I just find that S is the square root of x squared plus y squared. And that's the square root of, well, x is 60, so 60 squared plus 80 squared. And that is the square root of, let me see, that's 3,600 plus 6,400. So that's 10,000. Yeah, 10,000. And that is just 100. Yeah. Sorry. Yeah, that's right. Okay. So I suppose it should be 100 feet. But really, in this case, of course, we're going to focus on the numbers. Okay. Okay. Oh, boy. So we had this big, scary formula for dsdt. All right. And we were like, okay, this is nice because we've isolated dsdt, but we have all these variables. But we have found all the variables, so let's go ahead and plug them in. So let's see, I had 2x dx dt, so that's going to be 2 times 60 times dx dt was 20. Plus now 2y dy dt, so 2 times 80 times dy dt was 4. All over, I think we had 2s, and s is 100, so we have 2 times 100. We have 2's all over the place, so that will help us in our computation. We can cancel those. 60 times 20 plus 80 times 4, all over 100. And let me see, 60 times 20, that is 1,200. 80 times 4, that is 3,200? Yeah. And then, oh no, that's 320, excuse me, 320, okay. Now, that worried me because I know what the answer is supposed to be, and I wasn't getting the answer I was supposed to. But now I am, okay. So this is going to come out to 1520 over 100, and that comes out to 15.2. I suppose our unit here is going to be feet per second. Oh, 15.2 feet per second. Okay. So let's review real quick. We were given this picture and we were given this beautifully written story. Usually the first thing that you're going to want to do is figure out what the heck you're actually looking for, right? What quantity we're actually looking for. Here, we were looking for how fast the distance was increasing. Okay, so we're looking for a rate, how fast is the rate, is the distance increasing? So we saw that we wanted ds dt. Then we found a formula relating our variables. In this case, we we collaborated with our boy Pythagoras. We then took the derivative, which allowed us to find our quantity ds dt, which we could then isolate and solve for our variables using the beautifully composed story. And then we just did a little bit of plug and chug. Okay. Perhaps the hardest part of those problems is oftentimes just figuring out what you're looking for. And then from there, usually if you follow your nose, that will get you to a good place. Okay, so let me now go to the homework for this week. So now, or not this week, I should say, for today. So I'll go ahead and write homework just so that it's clear that we are moving on to those problems. Let me see, section 4.3, I had it pulled up, excuse me. Okay, now I have it again. We're gonna do, I think, 4 problems. There are 10 on the homework. A lot of them are very similar. So the first problem is number 2, and we are going to answer the following questions about the function whose derivative is f prime of x. I suppose I should write this nice and big and bold. F prime of x equals x squared times x minus 2 over x plus 5. And we are told that x is not equal to negative 5. That, of course, is because otherwise we'd be dividing by 0 and the math police would be after us. Okay. Part A then. So there's 3 things it's going to ask us about. First off, what are the critical points of f? Okay, so remember, critical points, those are going to be where f prime is either 0 or undefined. In this case, the only place where it might be undefined would be x equals negative 5, because that's where we would be dividing by 0. However, they have very graciously excluded that from our domain, so we don't have to worry about it. So, undefined, there are none here. So let's go ahead and set f prime of x equals 0, equal to 0. So let me see, 0 equals f prime of x equals x squared times x minus 2 over x plus 5. Okay, well, we can multiply both sides of this by x plus 5. And this is the same as saying 0 equals x squared times x minus 2, which means that x equals 0 or x equals 2. So these give us the x values for our critical points. So these are our critical points. I was looking, and I don't think it's asking us to find the y coordinates, but if we did, all that we would do is plug those x values into our function. So x equals 0 and x equals 2, those are our critical points. Again, all that we have to do is set 0 equal to that derivative, which is given to us. We would also have to check for places where the derivative is undefined, but here those do not exist. Okay. Moving on. Next, part B. Part B says, on what open intervals is f increasing or decreasing? Is f increasing or decreasing? And here's how we're going to do that. So the way that I'm going to start, at least, is we're going to draw a number line with all of our critical points, all of our critical, I guess I'll say critical x values. In this case, -5. We're including -5 here because the function behaves weird there, so we should also point that out as well. Okay, so let's go ahead and draw out our number line. It does not need to be to scale at all. The only thing that matters is that we get the order right. So let's see, we had x equals 0, x equals 2, okay. So let's go ahead and label x equals -5, so -5, and then we had 0 and 2. Okay, so then we're going to plug in points in each interval. Okay, when I say each interval, what I mean is, for example, this interval from -infinity to -5. So this interval here, the interval from -5 to 0, 0 to 2, and 2 onward to infinity. Okay, so that's what I mean whenever I say in each interval. And we're going to plug those into the derivative, so f prime. Okay. So for example, let's first look at what's happening to the left of -5. Well, f prime of, let's say, I don't know, what's a nice -10, I'll say. Why not? It doesn't matter. We can plug in anything we want so long as it is in this interval, to the left of -5. So if I plug in -10, let me see, that I'm going to get -10 squared times -10 minus 2 over -10 plus 5. Okay, and let's see. So this is going to give me 100 times -12 over -5. And the important thing here, we can go through and solve this and simplify it. But the important thing is that this is greater than 0. Okay, that is what matters. Let me emphasize that. Okay, this is the important part. How do I know it's greater than 0? Well, my numerator is negative and my denominator is negative. So they'll cancel, the negatives will cancel each other out. So what I'm going to do is I'm going to go up to my picture, and in that interval, I'm going to put a little plus. To me, that indicates that it's greater than 0. You don't have to use that notation. Heck, you don't even have to use this technique if you have another way that you prefer. But this is how I was taught, and I like the simplicity of it. Okay, so next up, let's move over to our next interval. So I want to pick something between -5 and 0. Since I have open parentheses, I don't want to include the endpoints. 0 is usually a great point to plug in, but we're not going to do that here because we're not including it. I'll go with -1. So that'll give me -1 squared times -1 minus 2 over -1 plus 5. Okay, so let's see. This gives me 1 times -3 over -1 plus 5 is 4. And this, I know, is going to be smaller than 0. Again, because the numerator this time is negative, but the denominator is positive. So between -5 and 0, the function is decreasing. Okay, so the plus, that means that the function is increasing. minus means the function is decreasing. Remember, the function is increasing if f prime is greater than or equal to 0, and decreasing if f prime is less than or equal to 0. Okay, so next up, we have this interval between 0 and 2, so let's go with f prime of positive 1, why not? 1 squared, 1 minus 2, all over 1 plus 5. So let me see, that's going to be 1 times minus 1 over 6. And this one is also going to be smaller than 0, because I have negative 1 on top over 6. Again, note it doesn't matter if we actually go through and compute exactly what they are, so long as we can tell if it's positive or negative. Okay, so this one is negative. And finally, let's plug in, let's plug in 5 for this last one. I don't care. F prime of 5. Okay, I just need something bigger than 2. 5 squared, 5 minus 2, over 5 plus 5. And that's going to be 25 times 3 over 10, and that is going to be greater than 0. It kind of looks like I wrote a 6 there, but that's true anyways, so. Okay, so we have our number line. We have now labeled it. You don't have to draw the interval, these parentheses here. I just drew that whenever I was talking about what I meant by the intervals, but usually I don't draw that. Again, whatever floats your boat, this is by no means a super fancy official technique. Just one way of organizing one's thoughts. So now we can answer this question of on what open intervals is f increasing or decreasing. Well, it's increasing wherever we drew plus signs. So it's increasing from negative infinity to negative 5. And I believe, again, it's increasing, from 2 to infinity. Okay, so we're going to make our union here. Remember the fancy looking U. And the function is decreasing from negative 5 to 0. Negative 5, 0, union with 0 to 2. If you wanted to, you could go ahead and include 0 and just write this as negative 5, we're not including negative 5, negative 5 to 2. If the derivative is 0, technically you can say the function is both increasing, or you can say it's either increasing or decreasing, because it's constant if f prime is 0, so it doesn't matter either way. It did ask for open intervals, so we do want to leave those parentheses open, but other than that, it makes no difference. All right, so that gives us that part. Finally, part C. Suppose I don't need to go back up there. Part C asks us at what points if any, does f assume local max and min values. Local max and min values. It said maximum and minimum, but I trust that you know what I mean. So at what points, if any, does f assume local max and min values? Let's look at max first. So this is informal, but I'm gonna write candidates for max. So this is going to be whenever f prime of x is greater than 0 for x less than a, and f prime of x is less than 0 for x greater than a, and f prime of a equals 0. Okay, so this is whenever a is a max. Let me change this phrasing. and say f has a local max at x equals a if this stuff is true. Okay? Whenever I say f prime of x is greater than 0 for x less than a, what I mean is over some interval. It doesn't have to be over the entire real number line. But like if I look just to the left of x, or excuse me, if I look just to the left of a, then the derivative should be increasing. The derivative should be positive, excuse me. And if I look just to the right of a, then the derivative should be negative. That's what I mean whenever I say for x less than a, or x greater than a. Okay? Now, again, I should note, or f prime of a equals 0 or undefined. In this case, again, we don't need to worry about undefined because we don't have any of those, but it is something that you would have to consider. You do have to consider it. So if we look at our number line, it looks like, so if I look at -5, it looks like there is going to be a max there because the derivative is, the function is increasing to the left of -5, and then it starts decreasing again after -5. Right, so at x equals -5, what's happening is the graph is doing something like this. This is -5. Because the derivative is increasing to the left, so it's positive, or excuse me, the derivative is positive, so the function is increasing to the left of -5. And the derivative is negative, so the function is decreasing to the right of -5. So, f assumes local max at x equals -5. And in fact, we can't actually compute what that local max is because we don't know what f is. All that we know is f prime. But even without knowing what f is, we can still see where it has local max and min values, and I think that's very interesting. Okay, so let's see if there are any other local maxes. It doesn't look like it, because if we look at our graph here, well, actually, it doesn't really assume a local max at x equals -5. Excuse me, this is false. Because f of -5 doesn't exist. Right? We specifically excluded it. Right? We specifically excluded it. Where is it? Here, x is not equal to -5. So it was important that we did that we included it in our number line, because that told us that f was increasing to the left of it. However, it actually does not exist. F of -5 does not exist, so there can't be a local max there. I hope that makes sense. It doesn't look like there are any other local maxes because there's nowhere else where to the left of a point the derivative is increasing. At 2, to the right of it, it's increasing, but not to the left of it. But that brings us to local mins. So f has a local min at x equals, I'll call it b this time, so that we don't get confused, if, and it's going to be very similar ideas. So now I want f prime of x to be decreasing, or f prime of x to be less than 0 for x less than b. I want f prime of x to then be positive for x greater than b. And I want f prime of b again to be 0 or undefined. Or wait a minute, hang on. No. Okay, hang on a minute. I just realized that I was being silly again. F of -5 does exist. F prime does not exist. Oh my lord. Okay. F of -5 exists. F prime of -5 doesn't exist. Okay. So actually, I apologize. What I wrote up here, that there are no places where the derivative is undefined. What I really should have said is x equals -5. I am so sorry. This is turning into a hot mess. Okay. Okay. So this is true that we have a local max at x equals -5. And it's the same reasoning here for why f has a local min in this case, because what this is saying is our graph is going to look something like this. It's decreasing, and then it's increasing. Okay, so that's why we have a min. And in fact, rather than b, let's go ahead and plug in x equals 2, because indeed, at x equals 2, the derivative is decreasing to the left of it, but then it starts increasing again. 0, the derivative 0 is this critical point. However, this is not a local max or min because the derivative is decreasing both to the left and to the right of it. Okay, so x equals 2. This is a local min. And while it doesn't ask for it, I want to note that x equals 0 is not a local extremum, meaning it's not a local max or min. At x equals 0, the derivative is decreasing, or the derivative is negative, and then the derivative is still negative. Something like that is what's going on there. Okay, so we got our local min at x equals 2, and our local max at x equals -5. Excuse me. Okay. Let's now jump to problem 5 on this homework. Problem 5. And this problem says find the open intervals. So this will actually be quite similar. However, we're going to have to compute the derivative this time, on which the function h of x equals x cubed minus x squared is increasing and decreasing. Okay, so this is our function. H of x equals x cubed minus x squared. This is actually 5a. Okay, so what we're going to do is we're going to compute h prime of x. And then from there, we're going to do basically the same kinds of things that we did before. So h prime of x equals 3x squared minus 2x. Okay, so first, let's find critical points. And remember, critical points, that is where h prime of x equals 0 or undefined. Now this time I am certain that there are no points where it's undefined, because if you look at our derivative, h prime of x, certainly I can plug in anything there, and I'm not going to break any math rules. I'm not going to divide by 0. I'm not going to take the square root of a negative number, etc. Okay, so let's go ahead and set this equal to 0 then. So 0 equals 3x squared minus 2x. So 0 equals, I can factor out x, and I'm left with 3x minus 2. So that means that x equals 0, or x equals 2/3. Okay, so these are our critical points. Okay. So, again, we're going to set up our number line. And let's label, in this case, we only have two values. We have x equals 0, and we have 2/3. Well, if I look to the left of 0, so if I look at, say, f prime of, I guess we have h in this case, h prime of -1, well, let me see, what does that give me? That gives me 3 times -1 squared, and then minus 2 times -1, and that is 3 plus 2 equals 5. And in particular, that is greater than 0. So that means I'm going to put a plus here to the left of 0. Okay, now I want to find something between 0 and 2/3. Well, that's not giving me much space. I'll go with h prime of 1/2. In that case, I'm going to have 3 times 1/2 squared minus 2 times 1/2. Let me see, that gives me 3/4 minus 1. And that's minus 1/4. And again, the important thing is just that it is smaller than 0. Finally, let's go ahead and plug in 1 to hit our highest interval above 2/3. That's going to give me 3 times 1 squared minus 2 times 1. And that's going to be 1, which is greater than 0. Boom. Okay, so now we can see that on the interval -infinity, so h increasing on -infinity to 0 and 2/3 to infinity, because those are the two intervals over which the derivative is positive. And h is decreasing, so h decreasing on this interval between them, it looks like from 0 to 2/3. So it's usually, in some sense, it is usually decreasing, right? Excuse me, it's usually increasing. Although I'll let you in on a little secret. There are just as many numbers between 0 and 2/3 as there are from -infinity to 0 union 2/3 to infinity. There are just as many numbers. So in some sense, when I say it's usually increasing or usually decreasing, really it's increasing and decreasing in equal amount, because math is crazy like that. But that doesn't matter. We found our intervals, and that is what matters here. Part B asks us to identify the functions, local and absolute extreme values, and absolute extreme values, if any, so there might not be any, saying where they occur. Now, in the previous problem, we were only able to identify the x values at which we had maxes and mins because we didn't know the original function. But in this case, we do know what h of x is, right? We're given h of x equals x cubed minus x squared. But we're going to use the same process to find the x values, and then from there, we will plug stuff in to find the y coordinates. So let's first look for maxes. Let's first look for local maxes. So if we look at our number line, Again, a local max is going to be where the derivative is positive and then it becomes negative. It looks like the only possibility there is going to be 0, right? Because the derivative is positive to the left of it and then negative. So this is going to be at x equals 0. Okay. And so let me see. So plug in, so x equals 0, then y equals 0 minus 0 cubed minus 0 squared equals 0. So 0, 0 is a local max. But now the question, what about global max? Well, if I look, so I see that the derivative is positive to the left of 0. Or tell you what, why don't we go ahead first and plug in why don't we worry about the global stuff in just a second? Because that's actually quite a bit more complicated. So let's first look at local min. If you look at the local mins, at x equals 2/3, I see that the derivative is decreasing. The derivative is negative to the left of 2/3, and then it's positive after 2/3. So it looks like we're going to have a local min at x equals 2/3. And at that point, we get that y equals 2/3 cubed minus 2/3 squared. And let me see, that's 8 over 27. 8 over 27 minus 4 over 9. So that's 8 over 27 minus 12 over 27, and that's going to be 4 over 27. So I have a local min at, this should be negative 4 over 27. I have a local min at 2/3 and minus 4 over 27. Okay, so I've got a local min. I've got a local max here. But I don't know what's happening as we go off to positive and negative infinity. I mean, we can figure it out, but the derivative information doesn't quite tell me enough. Right? I know that it's increasing to the left of 0. So let's sketch a quick picture with the information we do know. So we have this point 0, 0. We have this point, I'll draw it in pink. So we have this point, our local min, I'll draw it right here. Okay, so that's the pink point. And I know that the function is increasing to the left of 0, 0. So it looks maybe something like this. And then it's decreasing. And then it's increasing again. So it might look something like this. That's certainly one possibility. In this case, 0, 0 is not a global max because we see the function is getting bigger, right? Like this point here is bigger than 0, 0. This is higher than 0. So in that case, 0, 0 would not be a global max. And in fact, in this case, there is no global max because it's going to keep shooting off to infinity. And similarly, there is no local min because the farther left you go, it's always going to get smaller. Or excuse me, there is no absolute min. However, it's possible that our function instead looks something like this. It could be increasing, but ever so tiny. It could just barely be increasing, and then it could start decreasing, and then it could just barely start increasing again, and it could continue on like this forever. In this case, these two values, this 0, 0 and 2/3 negative 427, 4 over 27, those are also going to be global maxes and mins. Right? So we need more information, and what we're going to do in order to figure out what's happening to the left and right of these points is we're going to look at the limit as h goes to negative infinity, or excuse me, as x goes to negative infinity of h of x. H of x. Well, that's the limit as x goes to negative infinity of x cubed minus x squared. So now we'll do one of our favorite tricks, and we will factor out x squared. Limit as x approaches negative infinity of x squared, x cubed minus, excuse me, let's just be x minus 1 now. X minus 1. Or no, excuse me, what we want to do, we want to factor out by the highest power of x. So I want to factor out x cubed, and then I'll have 1 minus 1 over x. And so, as x approaches negative infinity, this is going to approach negative infinity, right? Because x cubed will approach negative infinity, and 1 over x goes to 0. So this is just negative infinity times 1. So this means that our 2/3 minus 4 over 27 is not a global min. In fact, there is no global min because the function is going to continue to get smaller and smaller as we shoot off, as x shoots off to negative infinity. So it never reaches a, quote, smallest point, it's always getting smaller. Similarly, the limit as x approaches positive infinity of h of x. I'm not going to go through the work here, but that is positive infinity. And that means there is no global max for the same reasons. All right. So that does it for this problem. The next problem on the docket is number 6, and this is going to have the same instructions essentially. So 6, it's just going to have a different function. So find the open intervals on which the function is increasing and decreasing. In fact, this is 6a again, which the function find the open intervals in which the function is increasing or decreasing, the function being f of x equals e to the 10x plus e to the minus x. Well, the first thing we're going to want to do, as before, is compute f prime of x. In this case, well, let's see, e to the 10x. So the derivative of e to the x, that's just e to the x. So this is going to be e to the 10x. And then I have to chain, so I have to multiply by 10 here, the derivative of 10x. Okay? And this is going to be minus e to the minus x. I'm not going to spend a ton of time on that now. That would be a good thing to review. If those derivatives aren't coming quickly to you, that's okay. But I figure that's not worth spending a ton of time on here in this video, since we talked about that a lot in a previous one. So our derivative is 10e to the 10x minus e to the minus x. And just as before, we want to find critical points. So find, what is happening? Find, hello? My pen might be close to dying. Let me try putting that in. Maybe that's why it's faltering a little bit. So find Hang on, I'm having technical difficulties with my pen. Maybe it doesn't like to charge and be written with at the same time. There we go, sort of. Find the critical points. Okay, my pen is, I think, dying on me. But we're so close to the end of the video. Come on, baby. You can do it. All right, my pen died, but we are back. I think we should be able to make it the rest of the way. We're almost done. This is the final problem of this video. I was gonna do one more, but time is of the essence. Okay, to find the open intervals, right. So the first thing that we want to do is we want to find the critical points of our function. So again, just as we've done before, we want to find where f prime of x is 0 or undefined. Well, it's clearly zero. It's clearly not the. It is clearly defined everywhere. There's nothing that I can plug in for x that will break mathematics. So instead, let's just go ahead and set 0 equal to that derivative and solve. Okay, well, this looks a bit ugly. Let me move that e to the minus x over, so I get e to the minus x equals 10e to the 10x. And now what I'm going to do is I'm going to take the natural log of both sides, so take ln both sides, and I get negative x. Remember, the natural log and e cancel each other out. So ln of e to the negative x is just negative x. Okay, and so now on the left-hand side, this is going to look a little bit different. So I'll have ln of 10 e to the 10x. Well, let me see. That's ln of 10 e to the 10x. Well, I can rewrite this as ln of 10 plus ln of e to the 10x. That's one of our fun logarithm tricks. And now the second one just comes out to 10x, and so this is ln of 10 e to the 10x plus ln of 10. Let me just go ahead. And that is equal to ln of 10 plus e to the 10x. Or excuse me, plus 10x. Blech. Plus 10x. There we go. Now we're talking. So now I can solve for x, and I get negative 11x equals ln of 10. So x equals ln of 10 minus ln of 10 over 11. Okay. So just like before, let's go ahead, draw our number line. The only point which we need to label this time is negative ln 10 over 11. Now let's see, is that going to be positive or negative? Well, ln of 10 is positive, so this is going to be negative. Right, so the 0 is over here. So I'll just make a note that this is less than 0. So that means that to find out what's going on to the right of it, I can just look at f prime of 0. Let's see, and that gives me 10e to the 10, 0. 10e, 10e to the 10 times 0 minus e to the minus 0. So this is just 10 times 1 minus 1, and that's 9, which is greater than 0. So the function is increasing to the right of negative ln 10 over 11. And I will be the first to admit that I don't know exactly what that is. But I do certainly know that, like, I think. Well, negative 1 actually is certainly smaller than that. Because ln of 10, so ln of 10 is smaller than 10. And how do I know that? We'll just raise e to both sides, and you will see that 10 is certainly smaller than e to the 10th. Right, so if you start with 10 less than e to the 10th, and then you take the natural log of both sides, that shows you what you want. So this means that minus ln 10 over 11 is bigger than negative 1, right? Because it's, let me write it this way, actually. It is bigger than negative 10 over 11, which is bigger than negative 1. So that allows me to just plug in negative 1, f prime of negative 1 equals 10e to the minus 10 minus 10 minus e to the first, and 10e to the minus 10. I'm going to have to use a calculator for this. So 10e to the minus 10 minus e. Okay, so that is negative less than 0. So I have negative here. This tells me then, okay, so first of all, this gives us our intervals on which the function is increasing and decreasing. Okay, I'm not going to write them out super formally here. You can put them together. All right, the function is decreasing to the left of this point and increasing to the right of it. Which means that my function, since that's the only critical point, my function necessarily looks something like this. Or I suppose it might not go up indefinitely, right? But I certainly know that I have a global min at x equals minus ln 10 over 11. I am not going to go through and solve at this point for what that is. So it definitely has no local max, no local maxes, or it actually can't have a global max either. No local or global max. Because it's constantly, as it approaches negative infinity or positive infinity, it's going to keep growing in either direction. Because limit as x approaches, well, yeah, no local max or global max. How do I want to say this? Because of the way that, because of the derivatives. Because of the derivatives. If you think, so I guess the point is, where could a global max possibly be? Well, if, say, I wanted to say the global max was here, right? Say I wanted to say the global max was at this green point. Well, I know to the left of it that the function is going to be bigger, so that can't possibly be a global max. But what if I wanted this point, this other green point, to be a global max? Well, I know that to the right of it, the function is going to be bigger, so this certainly can't be a global max either. So no matter where I am, I know that I can always find a point bigger. And so that's why there's no global max. All right, I was going to do one more problem, but in the interest of time, I'm going to wrap things up here. It basically would have been the same type of thing,